Hi everybody, my name is Neeraj. I'm a mechanical engineer and today I will be discussing with you the basics of computational fluid dynamics. So the main contents of this video are going to be the governing equation, boundary condition, discretization techniques and books. So let's begin. Hi, so in the first section of this video I will be discussing with you the governing equations that we use in CFD. So the main governing equations talk about mass conservation, momentum conservation and energy conservation. I will be discussing with you an isothermal and incompressible case where I will be walking you through the equations of momentum conservation and mass conservation. I will be explaining to you the physical meaning of those terms so that you can get a better understanding of these equations. So let's begin. Hi, so let's start our discussion for the governing equations for CFD. The main governing equations for CFD for an incompressible and isothermal case would be for momentum conservation and mass conservation. The moment I say momentum conservation, we have to look into Newton's second law, which talks about the rate of change of momentum is equal to the vector sum of all the forces acting on a body. Now we have to understand what kind of forces are acting on a fluid particle. It's either the body forces or the surface forces. On the left hand side we are taking a derivative of the momentum, which gives you the inertial forces, and that derivative is substantial derivative. By taking a substantial derivative we get two terms. The two terms are local derivative and the convective derivative. Now we have to understand the physical meaning of these two terms. So I will take the primary variable as temperature, or parameter as temperature, not as velocity, because to make you better understand this concept, temperature would be a better parameter. So let's say that I am a fluid particle and I am in a room and my location is fixed, and suddenly somebody has switched on an air conditioner. So my temperature at that particular instance would change. My location is fixed. So the local derivative talks about that kind of phenomena, where at that particular instance your value is changing. The primary variable's value is changing, or parameter's value is changing. Now with the convection term, I would like to take the same primary variable as temperature, and let's assume that I'm a fluid particle traveling from outside the room. Temperature outside is hot, let's say it's at a higher value, and I am arriving in the room which is at a lower value. Now as I arrive in the room, my temperature will decrease. Now that kind of a change, because my spatial coordinates are changing, I am coming from one place to another place, is represented by convective derivative. The condition in the room is different and I am changing my spatial coordinates, so that is represented by the convection term. Now for the right hand side we have body forces like gravity, electrostatic forces, Coriolis forces, centrifugal forces, and so on. For the surface forces we have pressure and shear forces. Here the shear forces we have represented in terms of velocity gradient from Newton's law. Now we have taken a volume integral on both sides. The need for taking a volume integral is because we are talking about a control volume. But Here I would like to point your attention to two terms, rather three terms. One is pressure, one is shear forces, and the convection term. For these terms, is there a meaning for taking a volume integral? I don't think so, because pressure acts on a surface, shear forces as well acts on a surface. Convection term also has a surface phenomena. So these terms, how we can take a volume integral, or how to go to the next step. So for these terms we have to use a very important theorem named as Gauss divergence theorem. These are my handwritten notes, and yeah, you can appreciate my handwriting. So in Gauss divergence theorem, you can see we are moving from a volume integral to surface integral. So for convection term, for the diffusion term, and for the pressure term, for these three terms we are moving from volume to surface. Rest is volume integral, body forces and the temporal acceleration. Now I will go to the mass conservation equation. Mass conservation talks about whatever mass is entering a control volume, the same mass should leave the control volume. For an incompressible flow, because density is constant, we need to worry about only the volume. We don't need to worry about the mass. We can only focus our attention to volume because density is constant. Now for this term, it is volume of fluid entering at a particular surface and volume of fluid leaving a particular surface. This talks about that kind of phenomena. That should be constant. And this is a divergence free velocity term. Divergence free, you can see it equates to 0. If there is a positive divergence, then it is a source term. If there is a negative divergence, then there is a sink term. But it is a zero divergence equation, so that means whatever volume of fluid is entering a particular surface, the same amount is leaving the fluid surface. So here also we have taken volume integral for the control volume, but here also we need to move from volume to surface. So in the next or the final form, you can see it takes a surface form, and the rest convection term, the diffusion term and the pressure term takes a surface form. I would like to tell you that the momentum conservation equation is famously known as Navier-Stokes equation. This equation is a second order non-linear PDE, partial differential equation. Here I have used tensor notations in I and J form. You can see here as well as here. For tensors, you have to understand that a scalar is a zero order tensor, a velocity would be a first order tensor, and shear stress or strain would be a second order tensor. Here you can see only one indices representation because velocity is a first order tensor. Now one law from tensor I would like to tell you, that if the tensor notations are repeating like here as well as in the continuity equation, if you take the divergence, then you will have to take a summation. If the tensor notations are repeating, then you will have to take a summation. That's a tensor law. So apart from this, I think this would be all for the governing equation. I think you got the physical meaning of the terms, and you got what kind of forces are acting and what is the physical nature, like whether they are acting on a surface, why we are taking the surface integral once we take the volume integral. And yeah, so that will be all for this part of my lecture. Thank you. Hi, so welcome to this section of the video on boundary conditions in CFD. Mainly there are two boundary conditions used in CFD most prominently. One is Dirichlet boundary condition, second is Neumann boundary condition. So first take essential boundary condition, which is also Dirichlet boundary condition. Let's take an example of a flat plate where this represents your boundary layer. This is the velocity profile at this section. The velocity in x direction at the plate is equal to 0, and this is represented here. This condition is known as Dirichlet boundary condition. It is very essential for you to enter this value while you are doing any simulation. So this is called as essential boundary condition. Let's take another example of a pipe flow. Here you can see, better I will zoom this. Here you can see this parabolic nature of velocity. This is for a laminar case, and this is your y direction, and this is your x direction. The x component of velocity at the wall will again be 0 at y is equal to 0 and y is equal to d. Y is equal to 0 is here and y is equal to d is here. So these two places, the x component of velocity will be equal to 0. This is essentially needed to solve the problem. So while you are doing a simulation, you need to enter these values. For Neumann boundary condition, we'll first take an example. Neumann boundary condition, also known as natural boundary condition. We will take an example from the flat plate. Again, here is your boundary layer. This represents your boundary layer thickness at this section. Outside boundary layer, your velocity gradient is 0. Your velocity is not changing. So here you can see at y is equal to delta, your velocity gradient is equal to 0. That means velocity is constant. This is a natural boundary condition, so this will be part of the mathematics involved in the problem. You don't need to enter this value while doing a simulation. I will take another example for making you better understand the Neumann boundary condition. This will be on pipe flow. Here you can see the two boundary layers for the pipe flow. Till the entrance length, your velocity profile keeps on changing, and this is for a laminar flow. So outside boundary layer, your gradient is 0 because your velocity is constant. Here also you can see outside boundary layer, your gradient is 0 and velocity is, because of velocity is constant. After the entrance length, you have a fully developed flow where you have a parabolic profile for the laminar case, and here the gradient becomes 0 at y is equal to 0, which is the center line of this pipe. So y is equal to 0, the x component of velocity is constant and the gradient is 0. This is a natural boundary condition which is known as Neumann boundary condition. So these two boundary conditions are most prominent, and I wanted to explain to you with examples. I hope you got the meaning of these conditions. Thank you. Hi everybody, I welcome you all in this section of my video, which is on discretization techniques. So first and foremost, we will be discussing about the purpose for discretization in CFD. For the purpose section, we will take an example of the parabolic profile of velocity for a laminar case. I have divided this into small domains. These domains would solve the purpose of capturing the gradients of the velocity. So let's say I choose a very small domain near to the wall, very fine domain it is, and in this domain you can see that the curve is exactly like a straight line, because we have a very small domain and curve behaves like a straight line. So when we take a gradient, which is a slope, this will be exactly like that curve, which is the velocity profile. So in this case, when we divide the whole domain into discrete control volumes, We want to capture these gradients. Near the wall we have fine mesh so that we can capture the steep gradients near the wall. So this is the main purpose, to capture the gradients of velocity, pressure, temperature, depending upon what equations you are using. For discretization techniques, I will be showing this image to you, which has three different form of meshes. The first one is called the structured grid, the second one is called the block structured grid, the third one is an unstructured grid. So let's discuss first the structured grid. The structured grid consists of entirely quadrilateral or hexahedral cells that have been arranged in an ordered array. So whatever the cells you are seeing here are all hexahedral and quadrilateral cells, depending upon a 2D mesh or a 3D mesh. Hexahedral will be for 3D mesh and quadrilateral would be for 2D mesh. But as you can see, if you do a fine mesh near the wall, then it will take the fine mesh all over the domain. So that is not advisable. Let's say I need very fine mesh in certain areas where I need to calculate the steeper gradient, but in the other areas where the gradients will be smooth, we don't need to have a very fine mesh. For that kind of purpose, we need a block structured grid, where in certain sections you have very fine mesh, and in other regions, you can see here, you don't need to calculate for steep gradients, so you can have a bigger blocks, you can have bigger meshes. The unstructured grid consists of 2D triangles and tetrahedrals or pyramids in 3D. They have no implicit order, so they are randomly arranged. So as you can see in this image, the most accurate would be the structured grid. The unstructured grid would be less accurate, but it will take, the unstructured grid will take lesser time for calculations, and the structured grid will take a lot of time for your calculation. So this image is from a book which I will be mentioning while telling you about the books. It is from my university professor and it's a really good book. I will be telling you more about the book in the next section. So in this section I would like to stop here, because this is all I had to say in the types of discretization techniques, and what is the main purpose I have already told you. That's all. Thank you. Hi everybody, I welcome you all in this section of my video, which is on books. The first book that I would like to recommend to you is Lectures on Computational Fluid Dynamics by Professor Nikolai Kornov. He is my university professor, and this book I am recommending, or the main content are more into numerics. So if you really want to do well in CFD, you must have a very good understanding of numerical solutions. So for this book, I have studied this book for more than 2 years now. Another aspect which is really interesting for this book is it contains the turbulence part as well. So very few books have numerics as well as turbulence, and this book has turbulence extensively. So you can understand which models you are taking, whether you are taking RANS, whether you are taking LES, what kind of mathematics is there. You can understand very nicely from this book. So this is highly recommended from me. The second book I would like to tell you is Computational Fluid Dynamics by John Anderson. This is the first book that I studied around 10 years ago. The main aspect that I would like to say about this book is that it talks about mathematics of CFD in a very nice manner, the way in which it should be taught. In CFD, mostly we are dealing with partial differential equations. Fluid parameters are changing with respect to space and time. Mostly we have a lot of vector calculus, we have tensor algebra, and to deal with that you need a very good understanding of these mathematical equations, and this book lays you the foundation for understanding the mathematics part of the CFD in very nice. So this book you must study. Third book, Computational Methods for Fluid Dynamics by Ferziger and Perick. This book, why I am recommending, is because of its physics part. So when we are solving numerically, we must have a very good understanding of physics, because when we solve a problem, first comes the physical model. We have to understand the physical model of the problem, then we can derive the mathematical model from the physical model. So physics is very important. So this book talks about the physics part in very detail, and one of my favorite books, and it's light as well, so it's easier to carry. The fourth book, if you really want to cover turbulence and you want to lay the foundation of understanding turbulence, so this book is highly recommended by P.A. Davidson from the Oxford University Press, and this is excellent book for understanding the physics of turbulence. Turbulence is ubiquitous nature because you can see it happening everywhere around you. When you read this book, everything will become crystal clear about turbulence to you. You must study this book. These 4 books are highly recommended from my side. Yeah, that's all from this section. Thank you. Hi, so I have come to the end part of this video. I hope you understood clearly all the contents mentioned. So let's say that when we are understanding governing equation of CFD, which is a partial differential equation, you are going to reduce the PDE into algebraic form of equations. And when you reduce it to algebraic set of equations, then you can form a matrix and then you can put it in a code. So this is the normal methodology used in numerics, and when we understand the physical model first, then we can understand the mathematical model. This is the path we take in numerics. Once we calculate through our simulation the parameters like pressure, velocity, temperature, then we can compare them with the experimental result. Experimental techniques like PIV, particle image velocimetry, laser Doppler anemometry, hot wire anemometry, these are velocity measuring techniques. Then you have pressure measuring techniques like pitot tube, U-tube manometer. These are pressure measuring techniques. You can measure temperature also through thermocouples. So these parameters are measurable in the experimental domain. So once you get the result from the experimental domain, the numerical result will always be an approximate result. So you have to compare them with the experimental result. Then only you can say that, okay, my results are correct. So I hope you have understood all the contents mentioned. In the coming weeks, maybe I will try to solve or show you the methodology used in 3 different types of problem. There will be industry-based problem, one will be from fluid structure interaction, one will be from turbulence, another one will be from conjugate heat transfer. These 3 domains I would like to cover. Maybe in this month I would be able to make a video showing you the physics, showing you the mathematics part. Before that, you can like, subscribe and share this video. Thank you.